Welcome back. In this lecture we will discuss the transformer architecture. This uses what's called an attention mechanism, and it's a neural architecture that's used in the very popular BERT models that some of you may have heard about. Also note, even though this lecture might be in a block about, quote, recurrent neural networks, the transformer architecture is not a recurrent neural network, but rather an alternative to it. So here's our objective. So let's go back to the challenges with recurrent neural networks. So even sophisticated RNNs such as long short-term memory, the long-term memory is limited for very long sequences of information. Also, the relationship, this hidden state that we had among cells, prohibits parallelization in training. So the cells are dependent on each other. And we also had this question about how to perform the initial embeddings. And while that's not the primary challenge addressed by the transformer architecture, the embeddings are different compared to the standard RNN setup. So here's some of the key ideas. So one, let's get rid of this recurrence relation. We can't parallelize it. Let's just kind of be done with it. And two is let's capture this idea of the position in the embedding itself. And this is like really interesting because we are now able to talk about the different inputs in relation to each other based on the inputs themselves. And you'll see why a little later. This is kind of a really neat idea. This idea of attention weighting is a way of weighting similarity between items in a sequence. And now let's just dive right into the architecture. So, okay. We have this positionally aware encoding of the sequence data. And so we have all of these vectors for everything in the sequence, and each vector is a concatenation of the input and its position in a single embedding. We take that and we repeat it 3 times. And with each time it's repeated in this first layer, it's going into a neural layer or a series of neural layers, depending on the architecture. And one is for what's called the key, the other is called the value, and the third is for the query. So what happens, so those neural layers are giving you those 3 what we call transformations of the input. So you have 3 different transformations of the input. Now the first 2 of them, we're going to do a similarity comparison. So pairwise similarity between the inputs, between the key and the value. And so this is, the result of this is what's called attention weighting, and this is your key value matrix. And so there's some scaling, and also normally there's softmax that's at the end of the series of layers that do attention weighting. We've not included it in this particular diagram. Now the attention weighting is then combined with the transformation of the query in another neural layer that provides you the output. Now what's interesting here is the positional relationships between the different inputs, how important those relationships are to each other really starts to fall out in this similarity matrix. And that's what's kind of neat about the whole thing, because it's taking care of the positional encoding along with looking at specifically what needs to be related to what in the input through this concept of attention weighting, through this similarity matrix. Everything here is a regular neural network. There's none of this hidden state stuff that's between layers, and this is much more easy to parallelize than your traditional RNN architecture. Oh, and one other piece, what we showed here is what's called a self-attention head. And this is the neural unit of a transformer architecture, and we can have many of these units for different things if we want. So some considerations is pros, big thing here, easy to parallelize, captures long-range dependencies. Really famous example of this is the AlphaFold 2 transformer-based model created by Google DeepMind. Solved the protein folding problem with very high accuracy. And that leveraged the transformer architecture, and the reason why it performed so well, even outperforming previous neural networks created by DeepMind and others, was due to the ability to capture these long-range dependencies because of the transformer architecture. Now, probably the biggest downside of transformer architecture is it involves a quadratic operation because of this similarity matrix. You're comparing all the inputs with itself, essentially, and that's a quadratic computation. Now, in practice, this doesn't turn out to be such a big deal because of the ability to parallelize, especially through GPUs. But bear in mind, we wouldn't want the sequence to be unruly lengthy, because that would lead to very expensive computation in the attention weighting. So that concludes the lecture for the transformer architecture. Hope you enjoy the rest of your day.